Assalamualaikum everyone. My name is Tasneem Tabassum Nabila and last three digits of my ID is 376. So here are my team members Himel, Sakib, Brishti and Shomik. So today I'll be talking about multiplexing techniques in modern communication system. Okay, so in simple terms, multiplexing is a way to send more data using the same connection. This helps make communication faster, more efficient, and more reliable, whether it's in mobile networks, Wi-Fi, or fiber optic cables. Okay, next slide. Okay, so now I'm going to talk about the core idea. The main idea of multiplexing is sharing. Multiplexing combines multiple signals and sends them together through one channel at the receiving end. These signals are separated back into their original form. A simple example is a phone line carrying many conversations at the same time. Each conversation is kept separate, but they all travel together. This is important because resources like bandwidth and cables are limited. Multiplexing helps us use them efficiently without needing more infrastructures. Okay, so here are the techniques. So there are several key multiplexing techniques. First is frequency division multiplexing, or we can say FDM. So this divides the signal into different frequency bands, so multiple signals can be sent at the same time. Second, time division multiplexing, or TDM. Here, each signal is given a short time slot to transmit. Third, space division multiplexing, or SDM, and MIMO. Okay, so this use multiple paths or antennas to send data simultaneously. Finally, OFDM, which uses many small subsignals to improve speed and reliability. So, in conclusion, multiplexing allows us to send more data using fewer resources. It plays a key role in modern communication systems and helps support the fast, connected world we live in today. Thank you.
Hello everyone, my name is Nazmus Sakib Moon. My ID is 242151998. Now I am describing about on the topic frequency division multiplexing FDM. FDM means we divided the total bandwidth into separate frequency bands and each band carries its own signal. A classic example is radio and TV broadcasting. Different stations use different frequencies at the same time. In modern systems, FDM is used in cable TV, DSL internet, and satellite communication. In fiber optics, it is called wavelength division multiplexing. To avoid interference, we use guardrails, filtering, and proper frequency planning. Another topic is time division multiplexing (TDM). TDM means we divide the channel into time slots. Each user gets their own turn to send data. Psychogenous TDM, here the slots are fixed. It's simple, but if a slot is empty, that time is wasted. Statistical TDM, here slots are given only when needed. This makes it more efficient, especially when traffic is irregular. Applications, we use TDM in telephone system, digital tracking, and secular networks.
Assalamualaikum. I am Jinat Farzana Brishti, my student ID 2421531. Today I will talk about SDM and OFDM. First, in this slide we see SDM. SDM is a method where multiple signals are sent using different physical paths. This means channels are separated by space, not by time or frequency. An example is multiple core fiber. In multiple core fiber, one cable has many cores and each core carries separate data. This increases data capacity without adding more cable. Another example is MIMO wireless. In MIMO, multiple antennas send and receive data at the same time. This improves speed, signal strength, and reliability. Next slide. This slide explains OFDM. OFDM is a type of frequency division multiplexing where many signals share overlapping frequencies but do not interfere with each other. OFDM is useful because it reduces signal interface and use bandwidth. This makes data transmission faster and more reliable. OFDM is used in technology like Wi-Fi, 4G, 5G, digital TV, and DSL. However, OFDM also has some problems such as high power uses and frequency errors. These problems are reduced using modern signal processing methods. That's all from my side. Now I would like to invite my next team member, Himel.
Assalamu alaikum everyone. My name is Sakib Hassan Himel. My ID is 242153227. The Frontier, Advanced and Emerging Techniques. So, what's next on the frontier? Two exciting techniques. First, RSMA or rate splitting multiple access. It's a powerful, flexible way to manage interference in dense networks, essential for 6G. And then there is OAM multiplexing, which, using the orbital angular momentum of radio waves, think of it as twisting the signal into a vortex, creating new orthogonal channels. It's very promising for high-capacity free space optics. Both approaches aim to unlock new resource dimensions beyond the classic time, frequency, and space. The impact connecting our worlds. So, what's the real-world impact? Every day, you benefit from multiplexing. It enables your broadband internet, your mobile 4G and 5G connection, your Wi-Fi, and your streaming services. From an infrastructure perspective, it maximizes the capacity of existing fibers and airwaves, delaying or even eliminating costly physical upgrades. And looking forward, it supports the low latency, high throughput applications of tomorrow, like AR and VR, autonomous systems, and massive scale IoT. Multiplexing is the silent engine. Okay, I will invite my next team member, Shomi.
Hello everyone, my name is Moshe Rahman Shomik. My ID is 242152123. The slide before you, the future is shared, multiplexing in 6G and beyond, represents the great leap in telecommunication. For decades, multiplexing has been the silent engine of the digital age. It's what allows us to share a single medium, whether it's a copper wire, a fiber optic cable, or airwaves, among millions of users. But we are but as we move into the 6G era, the traditional ways of slicing up time and frequency are no longer enough. In the future, multiplexing isn't just a background utility, it's becoming an intelligence driven, multiple dimensional ecosystem. We are moving beyond just sharing space to integrating time, frequency, power, and code into a single fluid resource management managed by artificial intelligence. Three pillars of 6G revolution. Number one, AI optimized multiple access (MA). These days of static configurations are over. With AI-optimized MA, the network no longer waits for a command, it predicts. By using machine learning to analyze traffic patterns in real time, the network can dynamically shift resources to whether they are needed most. This ensures maximum efficiency and perhaps more importantly, fairness, ensuring a seamless experience for a user in a crowded situation and a remote sensor in a rural field simultaneously. Number two, multifunctional networks. In 6G, the network does more than just talk. We are entering the age of integrated sensing and communication (ISSC). Image a world where the same signal that carries your video call also acts as a radar, sensing the environment around it to help autonomous vehicles navigating or to monitor city traffic. Where multiplexing communication data with radar sensing and edge computing, turning the network into a giant distributed brain. Number three is universal multiple access. Finally, we are striving for a universal framework. Instead of a patchwork of different standards for different devices, we are moving towards a single extensible architecture. This framework reconciles every dimensions of available
resources to meet the widely diverse demands of future. From the high bandwidth needs of holographic telescope to the ultra reliable low power needs of industrial IT. To wrap up, multiplexing remains the silent enabler of everything we do. Invisible architecture of our connected world. The techniques we are developing today are more than just technical specifications. They are the building blocks for a tomorrow that is obviously high capacity and truly shared. Thank you everyone for staying with us.